Hello, it's Keith here, and this is lesson 45 of the platform-specific series of my 68,000 assembly programming tutorials, and we're going to be looking at the NeoGeo today, and we're going to be looking at sound. Now, this makes for a bit of a weird thing because the NeoGeo actually has a Z80 processor, and it's only the Z80 processor that can make sound. So we're going to be looking at Z80 in our 68,000 tutorial, which might be a bit strange, but that's what we're going to be doing. So what are we going to be doing today? Well, we made something called ChibiSound before, which was a simple beeps driver for making simple beep sound effects. Today we're going to be making the Pro version, not entirely Pro version, but the slightly better version called ChibiSound PRO, which allows us to make simple music. The way it does this is it allows us more functionality. We basically pass 4 parameters, or 4 byte parameters in 3 parameters I should say. A 1 byte channel number, also with the top bit being noise on and off, a 1 byte volume, which is 0 for off and 255 for loudest, and a pitch from 0 to 65535, 0 being the lowest pitch and 65535 being the highest pitch. And so what we're going to do is we're going to use these to configure the channels, and my ChibiTracks music software uses these to play music. So that's what we're going to be looking at how to do. And of course the problem with the NeoGeo, as I say, is we have to do everything from the Z80 side. It's got a chip that's basically an AY sound chip. It's slightly more advanced, but it's backwards compatible, so we'll be using the AY functionality today. And so basically what we're going to be doing is we're going to need to send 4 bytes to the Z80, and the problem with this is we only have a single port that can transfer data between the two systems, and that's a 1 byte port. So what we're going to do is we're going to split those 4 bytes into 8 nibbles, and we're going to transfer, basically the top nibble is our command nibble and the bottom nibble is some kind of data, and we're going to do this in a way that is compatible with the original ChibiSound. The ChibiSound before did this as well, but that just needed a 1 byte parameter, but our new one is going to need a 4 byte parameter. So let's go and see what we're going to be doing. Over to our source code. Okay, well the first thing we're going to do is we're going to actually hear the wonders of ChibiSound PRO. So if I just fire up our oscilloscope here. So first we're going to run ChibiSound PRO test, which is just a basic test of the driver itself. So if we just fire this up here, speed up our emulator a bit. So we've got a tone here, and if I use up and down on the joystick, the simulator joystick here, you can hear the pitch changes, and we can enable noise with the fire button. Now that's just a very simple test program to allow me to actually check the driver works and debugging and wonderful things like that, and also to set the frequency table. But the far more interesting thing is that we can use this via my so-called ChibiTracks music software to play music, and this is a multi-platform music player, so it's not just 68,000 based, it's certainly not just NeoGeo based. It covers most of the systems in my tutorial, certainly all the 6502, 68,000 and Z80 ones. So here is the Chibi Akamas theme playing within ChibiTracks on the NeoGeo via the Z80. So there we go. So that's what this can do. Now what we're going to do first is we're going to look at the Z80 side, and we're going to discuss how we're going to process bytes on the Z80 side. As I say, we need 4 bytes to transfer. That's going to be transferred in 8 nibbles, and we're going to have to reconstruct those on the Z80 side. Then we're going to look at the 68,000 side and how we send that data. Then we're going to look back at the Z80 side at how we process that data and actually get the AY sound chip to do our bidding. Okay, it's a bit of a pain, but that's what it takes to get sound working on the NeoGeo. So whenever a byte is sent, we end up with an NMI interrupt at address 66 in hexadecimal. So this will be executed, and there are some of these that are basically firmware function calls, and so we're going to leave those well alone. All of our commands are going to have a top bit of 1. Now we have 2 original commands. The original one was 1000 for the top bits, and that was the first nibble of the ChibiSound driver. The second one was 1100, which was the second nibble of the original driver, and also that processed the sent byte. Now our new one is going to have to be a little bit more complicated. So we're going to have 3 commands. The first command is an initialization command, and that is going to be top nibble 1001. That is going to reset and tell the system we're going to send a new set of data. We're then going to have a sequence of nibbles, and these are going to have the sequence 1010, and there will be a number of these, and these will be the nibbles that we want to send to our driver. The final nibble will be 1011, and that will tell the driver to execute the bytes that were just sent. So we're going to have to send this sequence, and we're going to have various functions to process this data. Now all of this is in the top nibble. The bottom nibble is actually the data we want to process. Let's turn that oscilloscope off, it's quite annoying. So let's take a look. Okay, so here is the initialization byte, and I've been a bit future-proofy here. I've decided, oh well, actually this could happen again. Maybe I need a ChibiSound 2000 or something that's going to be even more advanced later. So let's use the bottom nibble of the initialization for some kind of parameter. So a value 0 here is the current ChibiSound PRO, but maybe something else might have a different branching out here to configure something else. Now once we've specified the command number, as I say, for future proofing, we're then resetting the position, and this is the nibble position, so we're setting it to 0, and we're branching over to this done routine here. This is basically going to send back a completion command. Now the completion command is that we write back the position number, which in this case would be 0, to the return port at port 0C here. So that is how we tell the 68000 side that we've finished. Now that would be just for the first instance. The other instances, we've actually got some kind of data. So we've received a nibble basically that we need to process. So of course, 2 nibbles for 1 byte. So what we're basically going to do here is we're going to get the address of the sequence here in HL. We're going to get the offset in A, but that is the offset in nibbles. So basically what we're going to do here is we're going to convert that into bytes by shifting to the right by 1 bit. And we're then going to add that to the HL offset for the byte that we actually want to change. Now what we're then going to do is we're then going to get the byte that we were passed, keep only the bottom nibble, and then we're going to check whether this is the first nibble or the second nibble. Now if it's the first nibble, then it's going to be the low part, the low nibble of the byte, and in that case we will carry on, but otherwise it's the high nibble. So in the low nibble case, we're just writing this byte straight into the destination because the high nibble hasn't been sent yet, and we're moving to the done position here. If it's the high nibble, we're shifting it into the high nibble position here with 4-bit shifts to the right here. We're then ORing in the byte that's currently in memory, and we're storing that new byte back into memory here. Now in that case, we're then jumping back to this done routine here, and what that is basically doing is it is incrementing the position of the nibble that we've just updated, and we're storing that back into memory, and then we are again sending the completion command back to the 68000. So that's how we're transferring our nibbles and reconstructing them in this memory address ChibiSound PRO bytes, which will be as many bytes as we want. As okay, in this case it's 4 bytes, but I'm thinking future proofing, you know, maybe we'll have a version with 16 bytes later on, who knows what we'll do in the future. So as I say, we've got this ability to send a different command number here if we want, and process larger numbers of bytes in the same way if we want to later on. The execute command is the final completion. Once we've sent all our nibbles, we want to actually do something with them. So basically here we've got a nibble here that is spare. So once again, we are keeping this as effectively a version number. So this should be a 0 for version 1, I guess. And then what we're doing here is we are loading in D and D from the first 2 bytes, and then H and L from the second 2 bytes, and then we're running the ChibiSound PRO set routine, which is our sound driver. Now the way that this will work is on the Z80 systems, it would work that basically the L register was the channel number and the noise on and off bit, and H was the volume, and then D and E were the pitch. And so that's what we're going to see in our Z80 code. We'll look at that in just a moment. So that's how we're reconstructing the data. Well, how are we actually sending it? Well, here is the ChibiSound PRO set routine, and what we've got is we've got a couple of commands to help us out. The most important one being the wait command. Now if you remember, we were actually sending back the command number that we had just processed whenever we were waiting, and so basically what we need to do is we need to wait for that command to be sent back to us. So we're reading in bytes from the Z80 side at this port here, and we're waiting to see when that matches D7, which is the command number that we're expecting to get back. And when it does, we're going to return. We're incrementing the command number when we get it back, but until then we're just going to keep waiting indefinitely until we get that command number back. So that's how we're waiting, and we're going to have to do that whenever we send any data at all. So our initialization, what we're going to need to do is we're basically going to need to send the initialization sequence with the bottom nibble as 0 to the Z80. That's what we're doing there. We're sending it, and then we're waiting for the response. That's command 0, so we're clearing D7 so that the matching command number comes back to us. And then when we want to actually send data, we're going to send it in two parts. We're going to send the low nibble of the byte in D0 first, and you can see we're ORing in the data command there, and then we're waiting here. And then the high nibble, we're basically taking the high nibble in D0, shifting it to the right by 4 bits, ORing in the command there to send data and sending that. Again, we're having to wait after each time. So whenever we want to load in a byte, for example, we are loading in the volume, which is a byte here in D3, we've got to do that twice. Once we send the low part and once we send the high part. So we're doing that in two parts there. And that's how we're sending the byte as 2 nibbles. And obviously if you send a word, then we're going to need to do that 4 times as we've done with D2 here. So we need to split our data up so we can send it in nibbles. And then finally, once we've sent all our nibbles, we're running the execute command, which is just sending that final sequence code there, 1011, with the bottom nibble as 0, just by definition here. And that is telling the Z80 to process all of the bytes in its array there and get on with it. And that's what's actually going to do the job. So that's the 68,000 side, and everything else we're going to do from the Z80. And so basically what we need to do is we need to deal with these registers here. These are AY registers, and they set the various settings for our channels. Now we've got 3 channels on the AY. My ChibiTracks music player was designed for the AY. So we've got basically pitches here. We've got a noise generator, a 5-bit noise frequency. We've got a mixer, and a bit of 0 in here will turn one of the channels on for tone or noise. And we've got the volume, which uses 4-bit volumes. And we're not going to use envelopes in today's example. The ChibiSound PRO driver doesn't do envelopes because it would be too complex to support on multiple systems. So we don't have that functionality available to this driver. Now, because of the way that the channels work with this mixer, we're going to use a lookup table to basically make it easy so that we can work out which bits we need to set for channels 0, 1 and 2 here. The other thing we're going to do is the way that ChibiSound PRO works is we're sending 7 bits theoretically for a channel number. We don't have 127 channels, funnily enough, so what we're going to do is we're going to have a lookup table to convert those. And basically the way that ChibiSound PRO works is channel 0 is the most important and all the following ones are less important. So if you're greater than channel 3, you can do whatever you want with them. So we're going to repeat between channels 0 and 2 for that, and we're going to use channel 1 for the first channel. The final thing we've got is we've got a cache of the AY data, and this was so that we didn't write data to the AY that was the same as existing data in case that caused interference. Now, when we want to set a register in the AY, we're going to use the AY write pro function. Now, this will set channel A, the accumulator, to value in register C. The first thing we're doing here is we're checking the AY cache and seeing if the value has already been set. And if it has been set, we're basically not going to do anything. If it's not been set though, we're going to update the value there, and then what we'll do is we'll write the register number to port 4, which selects the register on the AY sound chip, and then we write the new value to port 5. So this AY Read Write Pro will update the AY register and do nothing if the register already had that value we've been asked to set. We also have this do channel mask function. This will get in the channel number from L, and it will basically read in the mask from this entry here, so one of these, which is the mask for basically the mixer, for the bits in the mixer here. It will also point the BC register to the memory address within the cache of the previous value, so that if we need the previous value we can do things with that. Okay, so a bit of a faff there, but that's what we got. Now, when we want to actually set a channel, what we need to basically first do is we need to remap the channel numbers to the valid channel range. Now our lookup table has 8 entries, so we're taking the bottom 3 bits of our channel number and we're reading in a new channel number from that lookup table, and then we are ORing back in the top noise bit of the L register here, which is not the channel number. So we're basically using this as a remap here to remap our channels. So that's how we're dealing with our channel number at the very start. And then what we're going to do next is we are going to basically look at the volume, and if the volume is 0, then we're going to silence the channel. The way we do this is we get the channel mask and we basically mask the bits for the current channel. And then what we're going to do is we're going to OR those bits, setting them to 1 in the mixer. We're getting the current mixer value from BC, ORing those bits in, and this is basically so that we can turn those bits to 1, which silences the channel. A bit of 1 is the channel is off in the case of the AY sound chip. And so we're updating channel register 7, which is the mixer, and we're going to set those channels off. And at that point we're done. So in that case we would give up. If we're not done, we're going to process some of the stuff. Now you'll notice there's some experimental envelope stuff here. We're not covering that. That's not used by ChibiTracks. That was me experimenting in the early days when I was looking at what was possible. I decided that was beyond the scope of what I could port to other systems, so it's not supported by ChibiTracks, so we're not going to cover it today. What we're going to do next is we're going to set the frequency, and we're doing this from the DE pair. Now the frequencies, the way ChibiSound PRO works is a low value, a value 0 is a very low frequency, a value FFFF to 65535 is very high frequency, but it doesn't match on different systems, and so what we have is a lookup table of the octave to match the channel, the frequencies on different systems. And so we've got the notes here in the octave, and we've got the numbered octaves going down. And if we want a note like C sharp, what we would do is we would add those two values together and divide it by 2, and flats we do the same. So that's how we can get notes that match for musical purposes. So the AY sound chip, we actually need to flip that around though. A lower value is a higher pitch, and so what we're doing here is we're flipping the bits in DE. The other thing we need to do is we only want 12 bits here, so we're ditching 4 of the bits, and we're doing that with these bit shifts here. That's what we're doing there. And then what we're doing next is we are basically going to calculate the register numbers for our channel. So channel 0 uses registers 0 and 1, channel 1 uses 2 and 3, and channel 3 uses 4 and 5. And so what we're going to do here is we're basically going to double the channel number here, and then set the first register using basically the bottom byte here from E. And then what we're going to do is we're going to get the top register here, and then we're going to set the following register for the top byte of the tone pair there. So that's how we're setting the tone. Now what we'll do next will depend on whether we are wanting to enable the noise, which is set by the top bit of L here. If we are setting the noise on, we're going to need to set the channel mask differently, and we're also going to need to set the frequency. So in that case, what we're going to do is we are going to get the channel mask for the current channel. We are getting the bits for there, and then we're flipping the bits so that basically the two 1 bits became a 0, and this is because we want to basically clear those bits to turn the noise on and also the tone on. So we're storing that new value in D here, we're loading in the current value, and then we're ANDing that with our new mask, which is effectively setting the bits for the current channel to 0, and we're writing that back to the register 7, which is the mixer, and that's turning the noise on for this channel. Okay, so we've set our noises on there, but what we need to do is set the noise frequency now, and we're going to use the top byte of D, but to basically get it into the correct position for our noise frequency, we need to get 1 of the bits back from the low byte, and we need 5 bits in total. So we are basically shifting that in, and we are then setting register 6, which is the noise frequency, the noise generator here, and you can see that needs 5 bits, whereas we only needed 4 top bits for our frequency, which is why we're having to do that shift there. So that has set our noise, and in that case we're now done. If our noise is off though, we're doing something different. What we're doing is we're doing the get channel mask again, and we're masking the bits here that relate to the noise, because we want to set that to 1 to turn the noise off, and we're storing that in E. But then what we're doing next is we're getting the bottom bits here, and we're basically going to flip those because we want to set that bit to a 0, and we're storing that in a D. We're then loading in the current value, masking with our mask to set the tone bit to 0, and then ORing in to set the noise bit to 1, turning the noise off, turning the tone on, and we're storing that new value in C here, and we're sending that to register 7, which is the mixer, and that's turning our noise off and our tone on. Whichever we're doing, noise or tone though, we need to set the volume, and so we're loading in the value from H, and we're keeping only the top 4 bits because our volume is set by just 4 bits here. That's our volume there for our channels there. The channel registers start from 8, and so what we're going to do next is we're going to basically take the bottom 2 bits of our channel number, we're going to add 8, and then we're going to run the AYReg write pro here, which is going to set the volume for the correct channel. And at that point we're done. As I say, there's a few bits for envelopes, not covering them at this stage. It's not supported in general by the ChibiSound PRO driver. That was experimental stuff I was messing around with, but as I say, it's way outside of what I'm looking to do at this stage. All very complicated, I know. I've gone through it a little bit quickly, but that's the end of this lesson. If you like what you've seen, please like and subscribe. If you want to see more of this content, you can consider backing me on Patreon, because I'm really going out there with more and more complex tutorials, which takes more and more time and generally gets more and more stressful and means I feel less and less inclined to keep doing it. So if you want to keep seeing this content, please consider backing me. But anyway, if you've enjoyed what you've seen, go to the website, download the source code, build scripts, and use it in whatever way you can in your own projects. As I would say, you're welcome to do so. You don't even need to give me credit, because I'm nice like that. I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.